Imagine waking up on a world where rain falls quietly from orange clouds. But the rain is not water. It's liquid methane, cold enough to freeze you solid in seconds. Picture lakes and rivers that shimmer not with H2O, but with hydrocarbons, beneath a copper-tinted sky so dense you could almost swim through it. This place exists. Titan, Saturn's largest and most mysterious moon. And just this year, new discoveries from the James Webb Space Telescope, backed by a legacy of daring missions, are making scientists rethink not only Titan, but the very conditions that could foster life in our solar system, and possibly across the universe. What secrets are hidden in Titan's alien storms? How could they change our search for life? And could understanding Titan's weather rewrite our understanding of planetary habitability? Get ready. What we find on Titan might just transform how we see the cosmos and ourselves. Let's step back. Before we can grasp why these new revelations are so electrifying, we need to understand what makes Titan unlike anywhere else. Since the earliest days of planetary exploration, Saturn's moon Titan has loomed large in the imagination of scientists. For decades, all we knew was that it was big, nearly half the size of Earth, and so shrouded in mystery that visible light telescopes could barely pierce its thick orange atmosphere. What made Titan so fascinating was not just its size or its surface hidden under perpetual haze, but the weird clues it gave about its environment. Scientists suspected, from fleeting glimpses and indirect measurements, that something truly alien was at play. Titan's environment is, in a word, bizarre. Its surface is colder than 179 degrees Celsius, cold enough that water ice is hard as granite. But astonishingly, in these frigid conditions, Titan boasts rivers, lakes, and even seas. Here's the twist. Those lakes aren't filled with water. They're filled with liquid methane and ethane. These hydrocarbons, which on Earth are gases and even used for fuel, flow freely as liquids on Titan's surface. Imagine standing on the shore of a methane sea, mist curling off the surface, orange twilight above. But it gets weirder. Titan's atmosphere is thick and heavy, made mostly of nitrogen, much like Earth's air. But instead of the 78% nitrogen and 21% oxygen we breathe, Titan's air is about 95% nitrogen and 5% methane, with barely a hint of oxygen. The pressure at Titan's surface is about 1.5 times Earth's at sea level. It would squeeze you, but not crush you. And because gravity is just 1/7 of what you feel on Earth, you could jump higher and move with a strange, dreamlike lightness. This dense, cold nitrogen-methane atmosphere gives rise to something utterly unique in the solar system: Titan's methane weather cycle. On our planet, water evaporates from oceans or lakes, forms clouds, and falls as rain. Titan's version operates at a completely different chemistry, but eerily similar in process. Methane evaporates from Titan's surface lakes and seas, drifts up through the hazy atmosphere, condenses into dramatic clouds, and sometimes falls as a freezing, oily rain back to the ground. This one fact, weather, driven by a cycle, on a world other than Earth, is so rare that Connor Nixon, planetary scientist at NASA, put it bluntly: Titan is the only other place in our solar system that has weather like Earth. Yet for decades, direct evidence of these processes was frustratingly out of reach. The only spacecraft to land on Titan, the legendary Huygens probe, touched down in 2005 after a death-defying descent through the haze, beaming back the first, and so far only, surface images from Titan's frozen plain. Huygens showed pebbles apparently sculpted by liquid, and evidence of ancient dried riverbeds, suggesting rain had fallen sometime in the past. Orbiting overhead, the Cassini spacecraft mapped Titan's surface with radar, revealing gigantic seas near the poles, mysterious dark dunes stretched for hundreds of kilometers, and surface features that changed ever so slowly with Titan's glacially paced seasons. But still, the details remained fuzzy. The mirrors of modern telescopes and planetary probes can peer through the gloom, but to truly witness Titan's weather, its clouds forming, rising, and morphing from season to season, required new instruments and, crucially, patience. Titan's year lasts nearly 3 decades. A single season stretches across 7 Earth years. To catch the drama of Titan's atmospheric changes, scientists needed to watch and wait. That's where the James Webb Space Telescope, launched in 2021, comes in. With its powerful infrared eyes, Webb can finally see through Titan's haze and track its weather in action. In July 2023, Webb, working in tandem with the Keck 2 telescope on Earth, spotted something never clearly seen before: active, convection-driven clouds in Titan's northern hemisphere. These clouds weren't just sitting at one level, they were rising to new altitudes, confirming for the first time that Titan's methane weather, like Earth's water cycle, includes the turbulent updrafts that create storms and potentially rainfall. Why is this so important? For one, most of Titan's lakes and seas are clustered at these high northern latitudes, making them the heart of Titan's methane cycle. The clouds Webb observed suggested that methane is actively evaporating from these northern lakes, fueling the planet's weather. If Titan's weather cycle is active and dynamic, then Titan is not a static, frozen world. It's evolving before our eyes. Digging even deeper, the Webb telescope made another scientific breakthrough: the detection of the methyl radical, or CH3. This molecule is a fleeting intermediate step in the breakdown of methane in Titan's atmosphere. According to Dr. Stephanie Milam at NASA, for the first time we can see the chemical cake while it's rising in the oven, instead of just the starting ingredients. Scientists can now witness the ongoing chemistry in Titan's skies, an unprecedented opportunity to study processes key to the origins of life, but in an entirely alien context. Let's pause for a moment. Titan's methane weather is not just a curiosity. It's a living laboratory for planetary scientists and astrobiologists, a place where the same physical laws that sculpt Earth's clouds, rivers, and lakes are at work, but with a completely different chemistry. The stakes are enormous. If we can understand how complex weather and organic chemistry operate together on Titan, we might begin to answer one of humanity's oldest questions. How common are conditions suitable for life elsewhere in the cosmos? But there's a complication, a mystery, and a challenge. Methane on Titan is a limited commodity. Here's why that presents a problem. On Earth, water is constantly recycled by volcanoes, weathering, and planetary processes. But on Titan, methane in the atmosphere is constantly being destroyed by sunlight and cosmic rays. When methane molecules break apart high in the atmosphere, some of the hydrogen they release escapes into space and is lost forever. Without a source continually adding new methane, Titan's atmosphere should have run out of this crucial gas long ago. Instead, there's still plenty, enough to maintain its unique hazy orange shield and fuel its weather year after year. How is this possible? As Dr. Connor Nixon explains, methane is a consumable on Titan and may be constantly resupplied from the crust and interior over billions of years. But scientists don't know the source for sure. Some evidence suggests that Titan's icy crust may hide reservoirs of methane, perhaps even replenished from a mysterious, ammonia-rich subsurface ocean. Periodic geological activity might release new methane, recharging the atmosphere. Alternatively, the process could be winding down, meaning Titan's golden age of weather is a fleeting chapter in its long history, destined to end as the world becomes a desert of dust, dunes, and fading clouds. There's another twist. As methane breaks down, some of it turns into ethane, which cannot easily evaporate. Titan's lakes and seas, especially those nearer the poles, show variations in composition, some richer in methane, some in ethane. According to planetary scientist Ralph Lorenz, the wetter regions nearer the poles should have more methane relative to ethane in their lakes than would lakes in drier regions. This spatial patchwork gives scientists clues about Titan's weather, chemistry, and perhaps even changing climate. But the mysteries pile up. Why are Titan's lakes almost perfectly smooth, with waves measured in mere millimeters? Has Titan experienced catastrophic methane rainstorms in the distant past, or does its thick, oily atmosphere suppress violent weather? Webb and Keck observed clouds but no direct precipitation. Does rain only fall in certain seasons? Is Titan entering a period of climatic change, perhaps caused by cycles we barely grasp? And ultimately, the biggest question looms. Can the same processes that sustain Titan's exotic weather also create the precursors for life? Organic molecules, methane, ethane, even more complex hydrocarbons, are everywhere on Titan. If you look beneath its frozen surface, could there be evidence for life's building blocks, or even primitive life itself? The coming years promise new answers, and possibly even bigger questions. The upcoming Dragonfly mission, a nuclear-powered drone scheduled to land on Titan in 2034, aims to sample the surface, fly across dunes and seas, and directly analyze Titan's chemistry. As Dr. Heidi Hamel puts it, by combining all of these resources, including Webb, we maintain continuity between the former Cassini-Huygens mission and the upcoming Dragonfly mission. But for now, Titan's weather is a cosmic riddle, alive, evolving, and hinting at possibilities we are only beginning to imagine. So where does the methane come from, and what could its presence, or eventual disappearance, mean for Titan's long-term fate? And if Titan's weather system is so active, how might it be seeding the moon's surface, or even its underworld, with the building blocks for life? As we peer deeper into Titan's swirling clouds, we're forced to ask, is this bizarre world a preview of alien habitability or a cosmic dead end? And when Dragonfly finally arrives, what will it find in the shadowy dunes and hidden lakes? The true stakes of Titan's weather are only just coming into focus. As we gaze into Titan's cloudy depths, the questions grow more tantalizing. What will the new data, and the missions still to come, actually reveal about this enigmatic world? Will we finally understand the origin of Titan's methane, and could the answer hint at life beneath those alien clouds? The James Webb Space Telescope has opened a new chapter, but perhaps the most thrilling pages are yet to be written. The methane weather system observed by Webb and Keck isn't just a curiosity, it's a puzzle piece in the grand story of life's possibilities elsewhere. If methane is constantly replenished from Titan's interior, it suggests an active, dynamic moon. If it's running out, Titan could be on a slow march toward desolation, a preview of what happens when a planet or moon loses its protective, life-enabling atmosphere. Imagine for a moment the future that lies ahead. The Dragonfly mission, NASA's daring rotorcraft lander, is set to arrive on Titan in 2034. Its 8 rotors will whisk it across dunes and frozen plains, allowing it to sample varied locations in search of prebiotic chemistry and perhaps even biosignatures. For the first time since Cassini-Huygens, humanity will again set down on Titan's surface. This time, with technology far beyond that of the 2005 Huygens probe, Dragonfly will carry sophisticated instruments designed to analyze Titan at the molecular level. Scientists like Dr. Connor Nixon at NASA Goddard stress the importance of this continuity. By combining all of these resources, including Webb, we maintain a link between what Cassini saw and what Dragonfly will discover. One of the most profound consequences of these investigations could be a breakthrough in our understanding of planetary habitability. Will Dragonfly find organic molecules coalescing into something akin to life? Or will its instruments find that Titan, despite its Earth-like methane weather, remains just shy of life's spark? And if Titan, the most Earth-like moon in the solar system, has not managed to nurture life, what does that say about life's rarity, or ubiquity, across the cosmos? The scenarios ahead are as dramatic as any science fiction, but grounded in hard science. In one future, Dragonfly uncovers clear markers of prebiotic chemistry, complex molecules assembled into structures that could lead, given millions of years, to something alive. This would be a paradigm shift, echoing through biology, chemistry, and philosophy. Life, or its preconditions, may not be an earthly fluke. In another scenario, the methane cycle is found to be waning. Dragonfly's sensors might detect lower than expected methane reserves, or evidence that the supply from Titan's crust is drying up. If so, Titan could become a frigid graveyard, its lakes evaporating to nothing, its weather silenced. And then there's the possibility of discovering evidence of a subsurface ocean, ammonia-rich, salty, and far beneath the icy crust. What if there are traces of heat, energy gradients, or even metabolic byproducts? Could Titan hide life in its depths, just as Earth's oceans conceal strange creatures beneath the ice of Antarctica? But the path ahead is not without risk. Space missions are fraught with peril, from engineering failures to the simple unpredictability of alien terrain. The Huygens lander succeeded, but only just. Dragonfly must operate in brutal cold, buffeting winds, and mysterious terrain. There's no guarantee we'll receive the answers we seek on the first try. Yet the opportunity is profound. By watching Titan's atmosphere with Webb, we catch the methane cycle in real time, as Dr. Stephanie Milam from NASA Goddard puts it. For the first time, we can see the chemical cake while it's rising in the oven, instead of just the starting ingredients. This means we're not just guessing at how atmospheres evolve. We're watching it happen, step by step. The implications stretch far beyond Saturn. Titan's story could help us model climate feedbacks on Earth, where methane is a potent greenhouse gas. It might even prepare us for the discovery of exoplanets with thick atmospheres, planets that, at first glance, seem utterly alien, but whose chemistry may echo Titan's methane-laden sky. What practical lessons can we draw from this? For one, Titan reminds us that the ingredients for life might be common, but their arrangement and evolution require just the right touch of cosmic luck and planetary conditions. The techniques developed to study Titan's thick, orange-tinged haze, high-resolution infrared imaging, atmospheric modeling, and even future robotic exploration are tools we can use elsewhere. Each advance in space science, from better telescopes to smarter AI for image analysis, feeds directly back into Earth applications, meteorology, climate modeling, even environmental monitoring. On a more personal level, Titan's story is a call to curiosity. It's proof that the universe still holds mysteries we're only just beginning to tackle. As you watch this video, remember, not so long ago we thought of Saturn's moons as dead, frozen worlds. Today, we know better. We find weather, rivers, lakes, and even rain, just not the kind we're used to. Dr. Emily Schaller of the University of Arizona puts it best. We can study the meteorological cycle on another planetary body involving a different molecule. That's not just a scientific achievement, it's an expansion of our imagination. If weather isn't unique to Earth, maybe life isn't either. The next decade will determine whether Titan's methane cycle is sustained from below or dwindling at the surface. With Webb's eyes and Dragonfly's wings, we are positioned to answer one of the great scientific questions. Can Titan harbor life, now or in the distant past? And what does its fate tell us about the long-term survival of habitable worlds, ours included? And here's a secret fact that even some space enthusiasts miss. The same processes that break apart methane on Titan, a slow chemical dance under the fading sun, also slowly stripped Mars of its water billions of years ago. In other words, Titan's fate could be Mars in slow motion, a warning for any world that loses its atmospheric shield. So, will the enigma of Titan's methane be solved? The answer is closer than ever. But, as with all great mysteries, each revelation opens new questions. Maybe life lurks in Titan's hidden ocean, or under its icy rocks. Maybe the chemistry is only halfway there. But with every observation and every daring mission, we are rewriting what's possible. If you've enjoyed this journey to an alien world, hit that subscribe button and ring the bell so you never miss the latest in cosmic discoveries. Share your thoughts below. Do you think Titan harbors the ingredients for life? What would you like to see Dragonfly explore first? The quest to decode Titan's secrets is just beginning, and you're part of it. Until next time, keep looking up, because sometimes the wildest weather and the